Swayam Prabha. Digital India. Educated India.
Welcome to this another session in our introduction to aerodynamics. And in this session, we will talk about another aspect or another source of drag on aircraft wings. And this source of drag is known as wave drag. So in continuation with what we have been talking about, so far you have, I hope that you have some idea about what is a finite wing, what is an infinite wing, and the fact that drag, of course, it is something that happens from different parts of the aircraft. But here we are looking at drag on the aircraft wing. We have looked at two kinds of drag already. One is due to skin friction drag, and the second was due to pressure drag arising from flow separation due to adverse pressure gradient. And today we will look at this, this third source of drag, which is known as wave drag. Now, whenever you hear the word wave, essentially we are talking about shock waves. For some of you who have gone through a little bit of aerodynamics text by themselves, they might wonder that if this wave drag is a phenomena that is restricted to supersonic vehicles, because waves, or in more particular application, we are talking about shock waves, they generally appear in supersonic flow fields. However, we will see that, of course, you need supersonic flow field to generate shock waves. But sometimes, if your vehicle is flying subsonic, but very close to the sonic speed, what can happen is flow in certain regions of the wing or the vehicle body can accelerate to supersonic conditions. Okay, so even though the vehicle is flying subsonic, so free stream Mach number is subsonic, but if you remember that in some portions of the wing, the flow accelerates. In some portion of the wing, the flow decelerates. So if your vehicle is flying at a Mach number that is very close to the speed of sound, these local accelerations in portions of the wing or even portions of the aircraft body, primarily the wing, we don't have so much flow acceleration on portions of the aircraft body, but again it stems from the geometry of these things. So if you are flying close to the sonic speed, of course you are flying subsonic, but the flow can accelerate and reach supersonic conditions, because of which some shock waves can show up. So we will go through these things. But at this point, I want to clear the idea that wave drag, of course, in supersonic flow fields, you have these oblique shock waves, expansion waves, and if you work out the pressure distribution on the wing and then you calculate the force in the direction of the relative wind, you get a component of that force due to pressure distribution, due to the shock wave structures, that will give you, the pressure drag. In this case, due to, since the pressure distribution is influenced by all these shock waves and expansion waves, we call it wave drag. However, even for subsonic aircrafts, okay, so even for subsonic aircrafts that are flying close to the speed of sound, local accelerations on portions of the aircraft wing can cause the flow to accelerate to supersonic flow conditions. And in some situations, that supersonic flow can terminate in normal shock, etc., and create conditions where the wave or the shock wave present in the flow field creates a drag force on the wing. We will see how that happens. So wave drag happens due to shock waves. While primarily shock waves are found in supersonic flow, even for aircrafts that are flying subsonic, flow can accelerate locally to supersonic speeds, generate shock waves, and can influence the drag on these wings. So that's the what we will talk about in this this lecture, and perhaps in the next lecture as well. Now I will switch on to presentation mode, and so if you see my screen here, a little bit of a recapitulation. So we are talking about drag on airfoils, drag on wings for quite some time now. We have identified two important sources of drag. One is the skin friction drag. that stems from the boundary layer effect that is close to the wall of the wing. The flow has a certain distribution. Okay, so at the wall, the flow speed goes to 0 because of viscous effects. We have said that under some conditions of Knudsen number, there can be slip effects, but we will not look into those right now. For most of your applications, you can assume that the velocity of the flow at the wall for a viscid flow field becomes 0. So this is the relative velocity between the wall and the flow becomes 0. And then the flow gradually adjusts the velocity profile so as to reach the free stream velocity over a certain distance. Of course, this distance, it's asymptotically reaches the free stream velocity. But then for more engineering applications, we define a boundary layer thickness such as, the distance that is required to adjust to 99% of the free stream velocity. In some texts, I have seen 95% as well, but it is just a matter of definition or convention. Now, if you see the way the velocity is changing, you see that we have a velocity gradient in the wall normal direction. And if you multiply that velocity gradient with the viscous coefficient, then you get the wall shear stress. And this wall shear stress multiplied by the area gives you the shear force, and that integrated over the whole area of the wing gives you the frictional force that is contributing to drag. We discussed that for laminar flow fields, the velocity profile in the boundary layer looks something like this, whereas in the turbulent boundary layer, now keep in mind the instantaneous velocity profile will not look like this. This is the time averaged velocity profile in a turbulent boundary layer. And here we see that the rate of change of velocity with respect to this y-axis is very high. As a result, the du dy at the wall for the turbulent flow field is much higher than that is for a laminar flow field. And the shear stress for the turbulent case is much higher because of this large gradient of velocity near the wall. And we have the similar kind of shear stress that contributes to skin friction drag for the turbulent flow field. So once again, you can have laminar boundary layer, you can have turbulent boundary layer. The velocity gradient at the wall multiplied by the viscous coefficient generates the shear stress. You can calculate the shear stress from that. And once you know the stress, you can multiply it by the area, get the shear force, and then integrate it over the surface, take the right component in the direction of the relative wind in this particular case, and you can find what is the friction arising due to skin friction effect. What is the force or drag arising from the skin friction effect? Once again, this boundary layer, we have not talked about boundary layer in details, but it is a thin region near the wall of these bodies immersed in flowing fluid, where these velocity gradients exist. In fact, beyond this thin region, there is the flow behaves almost like an inviscid flow field. So although there is viscosity, velocity gradients are not so severe, and you can apply inviscid flow field analysis to regions outside the boundary layer. So these are extremely exaggerated views of what is happening in this thin region close to the wall in viscous flows. Of course, we are saying thin, thick. These are not very specific statements. We will see that depending on Reynolds number, Mach number, etc. And also like there are many other conditions that determine whether these boundary layer is going to be thick or thin, whether boundary layer will affect the inviscid flow field outside in a very strong manner or in a weak manner, whether that interaction with the inviscid layer will feed back into the boundary layer and couple with it. So those things we will discuss, not in an introductory course, but perhaps in a like an intermediate course. At this point, the idea is to give you a flavor of all these various things that happen in aerodynamics. So we have looked at this thing already, skin friction drag. I'm just trying to recap a bit. And then comes this thing called the pressure drag. And we have seen that we use the qualifier due to flow separation. So pressure drag due to flow separation. This is something we have also studied. And we have said that, so if you look at here, this is perhaps, like a nice visual to remember when you think of pressure drag due to flow separation. So what is happening is you see that in this region, So if you consider this as the point A, this point as A, this point as B, this point as C, and if you zoom into what is happening in the boundary layer, remember this is a thin region near the boundary. Okay, beyond the thin region, the flow is uniform, but near the wall you have this gradient, and that's the boundary layer. So at A, insert A shows you the condition of the boundary layer at location A. Also remember that in the initial region, dpds is favorable. So pressure is decreasing as AC is increasing, but beyond a certain point, dpds becomes the other way. So dpds and AC is just a surface fitted coordinate system. It's just a way of saying that if you follow the surface of this airfoil, pressure is going to increase at a certain point, beyond something like that. And then what happens is you see that the boundary layer starts seeing this adverse pressure gradient, and at some point the du by dy term becomes 0. Okay, and beyond that we see something known as the reversed flow field. So you see that the boundary layer actually separates, and in this region we have something that we have talked about before. We say this is the separated region, and the pressure in this region is almost it's almost uniform, and often it is same as the pressure at the point where that separation is happening. So what happens is, so how does that contribute to this drag? Okay, how does it cause the pressure drag? Now if you look at this image, okay, this is pretty much showing you the pressure distribution on these say the top surface, and what it shows is, see, in the front part of the wing, pressure was high. Then as the flow accelerated, pressure reduced. If you think of Bernoulli's theorem, velocity is increasing, pressure is decreasing. And then again, beyond a certain point, your unfavorable pressure gradient is happening. So pressure is now increasing with S. In the case where the flow did not separate, sometimes it is not necessary that if you had adverse pressure gradient, the flow has to separate. It depends on the magnitude of this adverse pressure gradient. And if you think of implicit flow analysis without boundary layer, then the flow of course will not separate. In those kind of analysis, you see that if the flow is attached, your pressure in the rear side, so in this region, recovers to a certain level by which the pressure, so if you think of the pressure in this region, so that's the pressure acting on the front part of the wing, so that pushes the wing behind, but that is balanced by this large pressure that the flow actually recovers to. So you see this pressure and this pressure can balance each other. Okay, so this pressure and these pressures can balance each other. However, the moment you have flow separation, what happens is, suppose flow separation happens around this S. So the pressure flattens out and becomes somewhat equal to the point at which the separation has occurred, and you see that in this case the pressure in this the rear side of the airfoil does not reach the values shown by this dotted line. Okay, so it kind of saturates or stabilizes at this level, which is much less than with this red arrows. So let me just draw it with a different color. Let me draw it with blue. So for the separated flow, the pressure in this region is hardly much less than the pressure shown by the red arrows. So what is happening is, now you still have the same force from the front pushing the wing opposite to the direction of flight, or if you think of it in the direction of the relative wind. However, the force from this pressure distribution in the rear side of the wing is now much less than what you have from the front part of the wing. So then this results in a net force that is oriented like this from left to right. So this is pretty much the second kind of drag we talked about, known as pressure drag due to flow separation. Now in lecture and in the so also we have talked about this thing, that the laminar boundary layer whose profile we saw here and the turbulent boundary layer whose profile we saw here, you will see that the turbulent boundary layer resists separation. Of course, if the pressure gradient, if the unfavorable pressure gradient is too large, even a turbulent boundary layer might separate. However, we will see that a turbulent boundary layer is more resistant to flow separation for good reasons, whereas the laminar boundary layer is very prone to separation due to unfavorable pressure gradient. And part of the reason is, if you see for the turbulent boundary layer, the momentum near the wall of the momentum of the flow near the wall is actually quite high due to better mixing of these flow layers. On the other hand, in the laminar flow field, you see that the momentum near the wall is quite low. So the adverse pressure gradient is able to create a reversed flow in this region, whereas the same adverse pressure gradient has to overcome the resistance created due to this large momentum of field near the wall. So that is why turbulent boundary layers are more resistant to flow separation. And if you think of practical applications, the dimple on golf balls, for example. So when you add the dimples on the golf ball, what happens is, of course, the flow the boundary layer around the ball becomes turbulent. That increases skin friction drag through this higher bound velocity gradient near the wall. However, the turbulent boundary layer can now resist this flow separation. So what happens is, although skin friction drag has increased because of you have made your boundary layer turbulent due to the presence of those dimples, you are now somehow able to resist this mechanism of drag. Okay, the flow is either the flow is not separating at all, or the flow is separating under more severe pressure gradients, creating a smaller wake. So we will see what is a large wake, what is a small wake. I think we have already seen this in our previous lectures, that depending on where your flow is separating, if it is separating near the, it depends on where it is separating. So if it is separating, I think if you remember the flow over circular cylinder, we talked about subcritical, supercritical separation, etc. So depending on the size of the wake, so once flow separates, you have a wake region. So here you see there's a wake on the top region. Okay, so depending on the size of the wake region, your pressure drag will depend on that. So for the golf ball, even if there is a flow separation, the amount of wake region created because of the dimples is actually quite small. So the presence of dimples makes the boundary layer turbulent. That increases skin friction drag, but reduces pressure drag due to flow separation. So nonetheless, so this is what we have done so far. Today, we will start in our discussion on this thing called wave drag. As I already said, wave drag, due to the presence of waves, shock waves. Also, there are other kinds of waves, expansion waves are there, shock waves are there. Again, shock waves can be normal shock waves, oblique shock waves, etc. And really, you deal with waves in supersonic flow fields mostly. But again, as I said, even in subsonic vehicles that are flying subsonic, there can be local accelerations where the flow field can become supersonic and shock waves can happen there. Now, because of the shock waves, pressure distribution is affected. In some cases, it can contribute to drag. So we will see how that happens. Okay. Now this is again going back to one of our very initial discussions. I think you must have seen this slide by now several times. So this is the Mach number axis. This is the Mach number axis M, and Mach number by now is okay. So we already have it here. It's the the flow speed divided by the speed of sound. As I said, for aerospace engineers or aerodynamicists, the speed of sound essentially means the speed at which mechanical disturbances propagate away from the source that is generating the mechanical disturbance, of course, of small amplitudes. And this has some very important implications. Why do we deal with this? Why does the speed of sound enter into our discussion? Okay. Now the thing is, there is a very formal way to look at how Mach number enters the picture. Okay, how Mach number enters the picture, how Reynolds number enters the picture. We have not talked about Reynolds number, Mach number in detail, but you will see that if you these are called similarity parameters: Mach number, Reynolds number, Prandtl number. There are many of these numbers that will show up. And one very mechanical approach is to start with the governing equations. You normalize them, and then so we will go through that exercise at some point. And once in the normalized governing equations, we will see that these parameters come out as the coefficients. And the idea is these equations are controlled by these parameters. So if two problems have the same parameters, then their non-dimensionalized representations will be similar. So of course, right now perhaps this will not make too much of a sense, but keep in mind that Mach number, Reynolds number, something known as Prandtl number, these are known as similarity parameters. So if your aircraft is flying at 30,000 feet, you want to study what is happening in terms of the pressure distribution, the moment on around the CG, how the Reynolds boundary layer might behave, and you want to study it in the wind tunnel. What you have to do is you have to make sure that the similarity parameters for the problem in the wind tunnel are same as those in the free flight. Only then your experimental results, and keep in mind the non-dimensional results will match with the non-dimensional results from the free flight counterpart. So we will get into these things at some point, maybe not in introductory course in aerodynamics, maybe the intermediate one. But nonetheless, this is the Mach number axis, and this is Mach 1. You understand that on the left side of this is subsonic flow. On the right side of is supersonic flow. This is Mach number 5. On the right side of Mach 5, we have a special name for the supersonic flow. We call it hypersonic flow. On the left side, of course, this is the supersonic flow regime, less than 5, greater than 1. Now, in these images on the bottom, we show that special consideration. So I want to draw your attention to the small aspect that, see, even when your vehicle, so when your vehicle is flying at a Mach number, say less than 0.8, so there is again nothing very specific about this 0.8. Generally, if you're flying close to Mach 1, but less than Mach 1, so subsonic still, your flow field around the wing, although they accelerate on the top, and you can have local areas of Mach number 0.85, 0.89. What we are saying here is the Mach number is sufficiently less than some critical Mach number, because of which, although the flow, becomes greater than 0.8 here and there, but the flow never becomes sonic or supersonic. However, at some point, your free stream velocity can be such that you have a sonic condition on the wing at some point. In fact, we will see that Mach number has a very special name. So what I'm saying is, when your vehicle is flying, at a Mach number of 0.6, although the flow is accelerating in some portions of the wing and becoming, say, Mach 0.65, somewhere Mach 0.7, but it is never reaching Mach 1. Okay, so flow is still subsonic. So free stream Mach number is subsonic. Flow is accelerating here and there on the wing, but again, if you look all over these flow field over the wing, still your flow has, everywhere it is subsonic, although it can be more than 0.6. However, as you crank up your free stream Mach number, at some point you will have, for example, here I think they are trying to say that 0.8 is the critical Mach number. So below 0.8, the flow field over the wing stays subsonic. Above, at 0.8, flow at somewhere on the top surface of the wing reaches sonic conditions for the first time, and that is known as the critical Mach number. And then beyond this 0.8, so if you go beyond 0.8, you actually can have shock waves. So this is the important concept or the important piece of information to keep in mind, that even when your vehicle is flying subsonic, see, your M infinity is between 0.8 and 1.0, you see you still have the shock waves You see, you have a shock wave on the top surface, you have shock wave on the bottom surface. But interestingly, your free stream velocity is between 0.8 and 1. Okay, so this is because of flow accelerations. Because of the geometry of the wing, flow can accelerate. And since you are almost near Mach 1, your flow has accelerated. So if you see this region, so this dotted line is known as the sonic line. So, and inside this sonic line, this region is actually supersonic flow. Okay, that shaded red region is supersonic flow. So it's interesting that even though your vehicle is flying at subsonic speeds, less than 1, but since it is flying close to 1, so that is the whole idea. Since it is flying close to 1, there can be local acceleration regions where the flow reaches supersonic speed. As you see here, the flow has reached supersonic speeds on the top and bottom surfaces, and we see the presence of terminal shock waves. Okay, in fact, this is the source of wave drag for the subsonic aircrafts. On the other hand, for supersonic vehicles, say Mach number greater than 1.2, Mach number greater than 5, the pressure distribution on the surface of these bodies are strongly affected by the shock waves. In high-speed aerodynamics, you will learn these things, how pressure behaves across a shock wave, what is a conical shock wave, what is a wedge shock wave, what is a normal shock wave, etc. Sometimes you have something known as an attached shock wave. Sometimes you have something called a detached shock wave. All these kinds of things are there. So in those situations, like the supersonic flow fields, the presence of shock waves. So here you see we say oblique shock. Here it's still an oblique shock for a hypersonic or high Mach number vehicle. The shock wave is moving close to the body. So these things we will touch upon later in a course in high-speed aerodynamics. But what I want to point out here is because of these shock waves, the pressure distribution on these surfaces are affected. And then if you find the force on the body due to the pressure distribution, due to the shock wave structure, you can take a component in the direction of the relative wind, and that will give you pressure drag, or here, since the pressure distribution is strongly affected by the the shock waves, you can also call it wave drag. So in the supersonic flow field, wave drag has some connotation, whereas in the subsonic flow field, now this is not just subsonic, it is subsonic, but it is close to that Mach 1. Okay, so close to Mach 1, local pockets of supersonic flow terminating in normal shocks, and these normal shocks create flow separation when they impinge on the boundary layer, and then an effect similar to that pressure drag due to flow separation sets in, creating very large increase in drag, and also of the coefficient of drag, or drag coefficient. And we will see these things in the subsequent slides. This is something that we have touched upon briefly in the previous page. I do not want to get into these discussions. So this is something that we will talk about when we deal with these high temperature gas dynamics. Right now, it is just present there because it's an introductory course. We oftentimes do not get a chance to talk about things. The time runs out, so I have just thrown in this piece of information. It is relevant to drag, but at a very intermediate or higher than intermediate level, how these things can affect lift and drag. But right now, and this is here, just okay, let me talk about this first, and then I'll talk about what I'm trying to refer to these things. Okay, so here is a wing cross section in supersonic flight. Okay, now see, unlike your subsonic wings that look something like like a streamline shape with the blunt leading edge, cusp trailing edge, your supersonic wings are typically are of these kind of sharp profiles. And what happens is a supersonic flow, when it deflects, it creates shock waves or expansion waves. We will study these things in detail. So this is also like because we are talking about this wave drag. So let me just, so this is wave drag, keep in mind. So this wave drag thing happens due to shock waves. Now, shock waves typically are associated with supersonic flow fields, but shock waves can also supersonic flow fields can happen even in subsonic flight because of local accelerations. Okay, keep that in mind. Whereas in supersonic vehicles, of course, your free stream Mach number is supersonic to begin with, and there what happens is as the flow deflects. So here you see this is the surface of the vehicle. Let me change my color to blue. This is the the front surface of the vehicle or the wing cross section. This is the rear surface of the wing cross section. So you see that we have a shock wave. So this is an oblique shock wave, and this is a expansion wave. We will study all these things like why these expansion waves are like diverging from each other. Why are they not, coalescing and creating a very strong expansion wave? We will see all these things, okay? But that is part of high-speed aerodynamics. But we will see that if time permits, we will talk about these things as well. So in a supersonic flow field, so supersonic free stream flow field, okay, we have these oblique shocks, expansion waves. Again, a terminating oblique shock. So where flow, okay, so if you have, let me just talk about this thing briefly, that when you have a supersonic flow that is going across a corner like this, okay, say this angle is theta. What happens is we have these shock waves. Just a second. We have a shock wave. It's called the wedge, the straight line actually. Pardon my bifurcating shock wave. This is just a straight line, okay? This is a straight line. And this angle is known as the shock angle. And this happens for supersonic Mach numbers. So if your m infinity is greater than 1 to begin with, okay? So now in case of this wing cross section, you see that m infinity is greater than 1, and something like this is happening, okay? So flow is coming in, flow is coming like that, then it's seeing this deflection and it's bending like that, and so flow deflection is same as this angle, and then we have a shock wave due to that flow deflection. So here if you think of it, your flow again, here you can see that your flow is coming like this, getting deflected by theta. That's why you have a shock wave at angle beta. Here again you see you are coming like this, then you are getting deflected. So you are having that oblique shock here. Okay. On the other hand, this is just so that you guys have some idea of what happens, because again I said that sometimes you don't get a chance to go over these things if you go in a linear fashion. So I want to just introduce this thing a little bit so that you know what is there in the material in aerodynamics. So, and this is where you get an expansion wave. So a corner such as this is known as an expansion corner. What happens is when the flow goes over this one, it creates, instead of this one strong oblique shock, it creates something known as a lot of these very fine waves known as the expansion waves. Okay, expansion waves, because we will see that across these, your static pressure increases, whereas across expansion waves, your static pressure and other things actually decrease. Okay, also it's an isentropic process and other things are there. We don't want to get into those. So here you see the flow is deflecting its head away from itself. So that's known as an expansion wave. Okay. So these two waves have very different properties, the contraction wave and the expansion wave, or the compression wave and the expansion wave. So you see here, something similar to this is happening. So we have these expansion waves, and all these shock waves, expansion waves, etc., influence the distribution of pressure on the surface of these wing cross section. In fact, once you know the pressure distribution, you can calculate the resultant force. The force normal to the direction of the relative wind is actually the lift force. So the lift is actually generated because of this pressure distribution created by these shocks and expansion waves. Similarly, the force in the drag direction is also due to this force due to the pressure distribution. So once you know the wave structure, you know the pressure distribution. If you integrate the forces due to the pressure distribution, you get a resultant force. You resolve it normal to relative velocity, you get lift. You resolve it along relative velocity, you get drag. And in this case, you understand that this pressure distribution is primarily influenced by these waves, and hence, its pressure. You can calculate lift and drag just from that analysis. Now, on the bottom, we show something that is slightly different from this wedge shock. It's called a conical shock. It's an axisymmetric cone. The conical shock looks something similar to the wedge shock, but it has some properties that are kind of nicely different from the oblique shock properties. But we do not want to get into this. Typically, in a intermediate course in aerodynamics or high-speed flows, you will deal with wedge shocks. You see, this is a 2D wedge, and this is a axisymmetric cone. Both in supersonic flow fields, shock waves are generated. We see attached shock waves. Under some theta beta m combinations, we can also have detached shock waves. But nonetheless, these shock waves influence the pressure distribution, and that can be used to get the lift and the drag. So this is for the supersonic vehicles. Again, if you think of like the space shuttle entering at very high Mach numbers, oftentimes you have well, I mean, I should take back what I just said. It doesn't really depend on the Mach number. It depends on the combination of theta, beta, and Mach number. Sometimes we can have this thing which is known as a detached shock wave. See here, your shock wave is attached to the front part of the wing. Here, your shock wave is attached to the front part of the cone. But here, the shock wave there's a standoff distance, right? You see that this wave is not attaching itself to the front of this vehicle. And it's because of some thing to do with this theta, beta, and m. Okay, so under certain conditions of theta, beta, and the free stream Mach number, you will have a detached shock wave and things like that. But nonetheless, you will see that behind this normal portion of the shock wave, so this is still supersonic flight. This one is something we say is normal shock wave, normal to the direction of the flow. And these are oblique shock waves. So these become more and more oblique to the direction of the flow. So if the flow direction is like this, you see these waves are not normal to the flow direction, right? So in this region, flow direction is like this. Wave direction is like this. So we call it normal shock wave, because this wave is oriented normal or perpendicular to the flow direction. However, if you look in these regions, for example, if you look at interaction in this region, what is happening is your flow is still horizontally directed. So your flow is still like this, but you see that your the wave is no longer normal. So the wave is somewhat like this, and then we say this is the oblique shock interaction. Because of this difference in interactions at different positions of this wave, the flow field behind a normal shock wave is always subsonic. Flow field behind an oblique shock wave is, for the weak oblique shock wave, it is, there is a subsonic, supersonic situation that can arise. But in most cases in nature, we have the weak solution of the oblique shock, and the flow field behind the oblique shock is, supersonic. So all that consideration will affect the pressure distribution on the surface of this vehicle, and that will affect the drag on this vehicle. So you can also think of it as a kind of wave drag, okay, because this pressure distribution is strongly affected by the wave distribution. I do not want to get too much into. Okay, let me just talk about this thing slightly. So if you see for a normal shock, if P1 and T1, so this is looking ahead, because this is an introductory course. Sometimes it helps to know what is to come, but this will typically in IIT, our department, we teach it in the third year, high-speed flow fields or high-speed flows. In some places, the same course is known by the name compressible flow. or compressible aerodynamics. There we deal with all these shock waves and expansion waves, attached shock, detached shock, etc. So you see for these shock waves, if this is the static pressure and static temperature ahead of the wave, and this is the static pressure, static temperature downstream of the wave, if M is really large number, then the P2 is much higher than P1, and T2 is much higher than T1. Okay, static pressure and static temperature. However, if M1 is not hypersonic but still supersonic, we still have P2 is greater than P1 and T2 is greater than T1 for the normal shock. For the oblique shock, and oblique shock is almost the analysis you will see makes use of the normal shock properties, but there is a trick to converting an oblique shock to a normal shock and doing the analysis. On the other hand, in case of the expansion wave, conditions are actually opposite to what happens across normal shock waves. Okay, so we will see that in a later course, but at this point, I'm just trying to emphasize that the shock waves and the expansion waves affect the distribution of static pressure, thereby affect your lift and drag. Here, although I was not intending to go through this, I just want to still talk about this thing because still somewhat pertinent to your lift and drag discussion. So what happens is, you see, I said that T2 can become larger than T1 across this shock wave. If M is very high, then this T2 can become quite large. And you can see that at various temperature ranges, various things are happening. Okay, say from 0 to 800 Kelvin, nothing much happens. Okay, no reactions, no dissociations, no plasma formation. However, beyond 800, my vibrational modes of the molecules start getting excited. You will see that this means that the Cp, Cv, and these things start becoming functions of temperature. In high-speed gas dynamics, there is this topic called high temperature gas dynamics. High speed brings in the aspect of high temperature. Okay, you cannot deal with high speed and not understand the idea of this high temperature gas dynamics. So we will get into those things in detail again in a subsequent lecture, if not in this course, in the follow-up courses. But at this point, just I think get a flavor of what happens. Around 800 Kelvin, the vibrational modes of the molecules start becoming active, and CpCv, so we use the word thermally perfect. In this region, it's calorically perfect. Okay, CpCv are constants. Beyond 800 Kelvin, CpCv becomes functions of temperature, so thermally perfect. Above 2500 Kelvin, so why are we talking about all these temperatures? It is because of this thing, that across a shock wave, temperature increases, static temperature increases. In fact, you will also see that there's something called stagnation temperature, and across a shock wave or an expansion wave, the stagnation temperature does not change. We have not talked about what is stagnation temperature, but at this point, forget stagnation temperature. Let us deal with static temperature only. And you can see that for these for these very high supersonic flow fields across a normal shock, your T2 can actually become extremely high. If it becomes high enough to cross this temperature, 2500 Kelvin, oxygen will start dissociating into oxygen atoms. Around 4000 Kelvin. So if this shock has occurred at a certain Mach number that is, high enough free stream Mach number to cause T2 be in this range above 4000, what will happen is nitrogen will now start dissociating into atomic nitrogen. If the shock wave is so strong, and again, the strength of shock wave is kind of related to the upstream Mach number. So if you have a shock wave at a very high Mach number, your temperature jumps can be very high. If the T2 is in the range of 9000 or plus, so N2 is completely dissociated by this temperature, and beyond this, you have ionization. So this region is partially ionized plasma. So this is a very strange situation where the shock wave, so your vehicle is flying supersonic, and the supersonic Mach number is so high that the T2 behind the shock wave is becoming so high that all these effects are happening. And when all these effects happen, the distribution of pressure is somehow related to, what is happening with these with the composition and other things. Um, Temperature, pressure, everything gets affected by all these phenomena that is happening. So in that case, your lift and drag forces will start getting affected by the strength of the shock wave, okay, and hence by the Mach number at which the shock waves are happening. However, in this introductory lesson in aerodynamics, we will not get into all these discussions. At this point, just keep in mind, once again, as I said a moment back, that wave drag is due to the influence of waves. These waves appear only in supersonic flow fields. However, you might wonder, so in this slide, for example, we have talked about supersonic flow fields only. However, you might wonder that then why is it something wave drag is always just pertinent for supersonic flight conditions, or does it happen in subsonic vehicles as well? As I said, vehicle is flying close to Mach 1, but subsonic, you can still have waves, and that waves can still affect the flow field in such a way so as to cause a large increase in drag, and we give it a special name called wave drag. So we will see those in subsequent chapters. So wave drag can happen both for supersonic vehicles and subsonic vehicles. For subsonic vehicles flying close to Mach number 1. Okay. Now this is a very important concept. So now so in the previous slide we talked mostly about supersonic flight. Okay, the vehicle is flying supersonic. You have with these thin wing cross sections with sharp edges. You have shock waves, expansion waves. You work out the pressure distribution. From the pressure, you get the forces. From the forces, you get the resultant force. Resolve it normal to the relative wind. Along the relative wind, you get lift and drag, etc. On the other hand, if you are looking now at a subsonic, so the moment you see airfoil a wing cross section such as this, you can think of it as primarily a subsonic vehicle wing. And if you see the wing is thin, then wing has some special designs. For example, this one, it's a subsonic wing, but it is known as a subcritical wing. Okay, there are reasons why we design these wings, but nonetheless, just from the look of a wing, you can kind of guess whether it is for supersonic flight vehicle or for a subsonic flight vehicle, for a low speed subsonic or for high speed subsonic, and that is what will be evident from the discussions that will follow. So if you see, we are showing so first of all, we will get into the discussion of what is critical Mach number. Oftentimes you will see this thing called MCR. Okay, so that is M with the subscript CR, or the critical Mach number. So think of an airfoil as shown here, and think of this A at the point where somehow the point A has this special property that flow accelerates. So you have a stagnation point here. Then the flow accelerates, and then at some point downstream the flow decelerates. Favorable pressure gradient and unfavorable pressure gradient. Flow accelerates and flow decelerates, and at the point A, the flow velocity is the maximum. Okay, so when flow velocity is the maximum, pressure is the minimum. So at A, M is maximum, and pressure is minimum. Pressure is minimum. So what is happening here is, so when this wing is put, say you have put the wing in a wind tunnel, and you have cranked up the speed of the wind tunnel in such a way that the Mach number, which essentially is U by A, so what is the velocity of the wind tunnel cross section, or what is the velocity of flow in the wind tunnel, and what is the temperature of the day, so you can figure out what is A. So you calculate U by A, and you see it is 0.3. Now at this point A, where I'm saying the Mach number reaches maximum, you see that the Mach number has become 0.435. Of course, you understand that these specific numbers have to do with the specific wing cross section that we are dealing with. Okay, so the specific wing cross section will generate a specific Mach number at this point A, which we are saying is the point where the flow attains its maximum Mach number. Okay, it depends on the geometry of the wing. Now we crank up the velocity U, and we reach, say, M infinity of 0.5. Now I can also somehow reduce the temperature of the flow field and increase Mach number that way. But I think for people who are seeing these things for the first time, it makes more sense to think of it this way, that you're cranking up the velocity and hence you are increasing the Mach number. And now when your flow Mach number has become 0.5, you see that at this point A, where previously you were getting 0.435, you are getting a Mach number of 0.772. So you see that as you increase the free stream Mach number, your Mach number at this point A, where we are saying that this point A is the point where the flow reaches its maximum, velocity, or rather its maximum Mach number. And here we see Mach number of 0.772. Now, when we crank it up to 0.61, we suddenly see that the Mach number here has become Mach 1. So this is known as the critical Mach number for this particular airfoil. Okay, it doesn't mean that 0.61 is the critical Mach number, is like a universal constant. It's not the case. So Mach 0.61 is the critical Mach number for this airfoil, because when we crank up the flow to reach Mach infinity is equal to 0.61, the flow at that location A, where the Mach number is maximum, becomes sonic. So you see that although your free stream Mach number M infinity is 0.61, it's relatively subsonic. It's quite subsonic, to be honest. The Mach number at this location A is becoming sonic. In fact, if now you push the free stream Mach number above 0.65, you will see that a region of supersonic flow is established, and supersonic flow, and that terminates in a shock wave. And the problem is this shock wave imposes unfavorable pressure gradient. You remember that we showed that across a shock wave, static temperature increases. You remember this is T1, this is P1, this is the normal shock wave, this is T2, this is P2, and flow is going across the normal shock, say from left to right. Okay, so temperature T2 is higher than T1. Similarly, P2 is higher than P1. And it can be shown that stronger the shock wave, okay, stronger your M1, stronger are these T2s and P2s. So across the shock wave, your P2 across the shock wave is higher than P1. So this shock wave actually imposes unfavorable pressure gradient, okay, and it imposes unfavorable pressure gradient of sufficient magnitude so as to cause flow separation. So that is the important thing to keep in mind here, okay. So flow separation happens, and if you think of that idea of attached flow and separated flow, that caused that pressure drag due to flow separation, something similar you can think of is happening here, where the pressure distribution in the aft part is actually quite high, and the flow separates downstream of the shock wave, creating this separated region. And because of that, you have a large drag in the direction of the relative wind. Okay, so you see in this particular case, M infinity is greater than Mach critical, so which means that when it becomes Mach critical, you reach sonic condition and at some point of the wing for the first time. But when your free stream Mach number goes above Mach critical, then you actually have this pocket of supersonic flow field. Okay, in this particular case, you see that the supersonic flow field is extending over a pretty large area away from the wing. This whole area is supersonic. And of course, you have a relatively strong shock wave that is imposing a large dpdx or dpds. It depends on here S, so maybe dpds is a better thing to write. So it imposes a large pressure gradient because of which the boundary layer is separating. And you see that once you have the separation, you can think along these lines that your pressure drag is going to become significant. It is also the case that the Cp in this region, the pressure in this region, or the CP in this region. We will see the connection between CP and pressure shortly. Because of compressibility effects, your CP gets exaggerated. Okay, so CP actually becomes large because of these Mach numbers greater than 0.3. So when you operate between 0.3 and 1, you have to modify your CP to adjust for something known as compressibility corrections. Okay, so you have to correct for compressibility effects, and you will see that the effect of compressibility, say for the subsonic flow fields, but flow fields which are compressible, because remember, I don't know whether we have covered this thing in one of our initial slides, or maybe I'm waiting for, because I want to cover Rayleigh transport theorem before we get into the discussion of what is compressible flow, what is incompressible flow. But at this point, just keep in mind that, if you are trying to calculate CP for at a location, you have to, and suppose you have, okay, let me keep it for the next slide. I think so. What I'm trying to say is, we have a large shock wave creating adverse pressure gradient. We have flow separation. We have some situation like this. The reason for that pressure drag due to flow separation. But what I'm trying to say is, this pressure in this region is actually exaggerated because of the compressibility effect, and we will see what that means. So it's not only the pressure here that is, pushing it in this direction, but this pressure here, or rather the CP from related to the pressure, is increasing in such a way that the force is actually, so CP gets exaggerated due to compressibility effects, and you have flow separation due to these relative strong shock creating a ds greater than 0. So the flow separation creates the pressure drag due to flow separation kind of effect due to the wave, but this pressure on the front surface actually gets exaggerated because of compressibility effects, and we will see that. So CP gets exaggerated because of compressibility effects. Now you will see that sometimes we try to mitigate these problems by using some intelligent design. So for example, here we have something called the supercritical airfoil, and you see that the top surface is flat, and this results in a supersonic flow field that is relatively confined to the wing surface. And you see here the huge amount of flow area is subjected to the supersonic flow, whereas here you have a small area subjected to supersonic flow, and it terminates in a relatively weak shock wave, creating a small amount of positive dpdx. Okay, of course the shock wave still creates a large dpdx, but compared to this one, it's not a subcritical airfoil. It's not a subcritical airfoil. This is just a normal airfoil. However, for the subcritical airfoil, you see that something has been done because of which the flow does not reach very high supersonic flow Mach numbers, and also, so if it does not reach high supersonic Mach numbers, then it actually terminates in a weak shock wave. If it somehow reaches high Mach numbers, in this case, it terminates in a strong shock wave. So the supercritical airfoil, by there are some ways in which this thing it restricts the Mach number range of this region and also the extent of this region, and so the relatively weak shock creates a small region of the separated flow, and that results in a smaller amount of drag. So I think we will conclude with this much in today's lecture. So we have just started talking about this wave drag, and we will spend 1 or 2 more lectures on understanding wave drag. And so we will see you in the next class, and we will continue with this idea of critical Mach number, drag divergence Mach number, why the CD or the drag coefficient increases suddenly near Mach 1, etc. So see you in the next class. Thank you.